Good day, mate. Hello guys, it is Tatiana here, and today I am going to show you how I would approach / solve one of the previous free response questions. Well, I hope to shed some light on this problem and brighten up your day. Okay, so this is number 5 from the 2018 AP test free response. You can super easily find it on the College Board website. So here it is. Block P of mass M is on a horizontal frictionless surface and is attached to a spring with a spring constant K. The block is oscillating with a period Tp. TP. Toilet paper. Don't we wish we had that in the stores these days? Anyway, and amplitude AP about the spring's equilibrium position x0. A second block Q of mass 2m is then dropped from rest and lands on block P at the instant it passes through the equilibrium position as shown above. Block Q immediately sticks to the top of block P, and the two-block system oscillates with period TPQ and amplitude APQ. Okay, that was a lot of words and T's and A's and P's and Q's, so let's break it down. When reading the problem, there should have been one thing that really sticks out, and that is the word stick. The word stick should automatically make you think inelastic collision. It's super important to recognize that one block landing on top of another and sticking to it is in fact an inelastic collision. Okay, so my first step is to draw a picture, and even though we're already given one in the problem, I want to break it into two parts because at the beginning we have one block oscillating, and after the collision we have two. My first picture is just a singular block oscillating on a spring, and my second picture is the same except there are two blocks oscillating on the same spring. Okay, so for the first picture, I know that this is block P. The mass of block P is just equal to m. I know that the spring constant is K, and the spring has some equilibrium position, x0, and that is the position where the spring is completely unstretched. It wants to keep chilling at this position. It's not squished or stretched or anything. So this block is oscillating back and forth, and it has a maximum displacement from equilibrium. That is the amplitude. And for this block, it is A sub P. And we also know that this block is oscillating with a period of TP. Alright, so now for the system with two blocks. This top block, block Q, lands on top of block P while the system is passing the equilibrium position. That's super important. This system also oscillates with an amplitude of APQ. We don't know yet if that's different from AP. The spring is the same spring, so the spring constant is still K. And we know that the mass of block Q is 2m, and we already knew that the mass of block P is just m. And this system over here is oscillating with a period of TPQ. Don't know if that's different from the first system, but that is what we know. Okay, I'm gonna spring over to the paragraph portion of this problem, and it asks, how does the amplitude of oscillation APQ of the two-block system compare with the original amplitude AP of block P alone? So we need to determine whether the amplitude of the oscillating mass spring system changes when the second block is dropped on top of the first block. To do that, let's remember some stuff about springs first. So, you have this block here. It is oscillating back and forth about the equilibrium position of the spring. So in this position here, I have drawn the block at its farthest point away from equilibrium, so the spring is fully stretched, and we call this displacement from equilibrium the amplitude of oscillation. So at this instant in time, the block is not moving for a split second because first it was moving to the right and it needs to stop and turn around and come back. So if the block is not moving, we know that the kinetic energy is 0, and therefore the spring potential energy is at its maximum value, and that is equal to 1/2 Ka squared, where A is the displacement from equilibrium, and in this case that would be the amplitude. Now, the block then goes back to the left because the spring is pulling it back that way, and eventually it passes the equilibrium position. So at the equilibrium position, the block or the spring is not stretched or compressed at all, which means that the spring potential energy is equal to 0. However, all that spring potential energy that we had over here had to go somewhere because energy is conserved. So that spring potential energy became kinetic energy over here, and that means that the kinetic energy here is at its maximum value, and that equals 1/2 mv squared. Okay, and so the block will continue to the left and the cycle will continue. Okay, so here's how to solve the problem. When you first read the problem, I said that you should pay attention to the word stick, and from that understand that this is an inelastic collision. So I'm going to start with that. Inelastic collision. So when you hear the word collision, there's something very important that you should be thinking. Take a moment and think about it. And that's right, momentum. You should be thinking momentum. When you have an inelastic collision, momentum is conserved. What that means is the momentum at the beginning equals the momentum at the end, before collision and after collision. Before the collision, block P has horizontal momentum. It's moving left and right. Block Q does not have any horizontal momentum. So when it is dropped onto block P, it is adding no horizontal momentum to the system. However, it is adding its mass into the system. So before we had block P oscillating back and forth, and when block Q is dropped on top of block P, now the system just got more massive. If momentum equals mass times velocity, and the mass goes up, in order for the value of the momentum to stay the same, the velocity must go down. So the mass of the system increased. That means that the velocity of the system went down. Now, the key here is that block Q was dropped on top of block P when it was passing the equilibrium position. Now, we talked about earlier that at the equilibrium position, the kinetic energy is at a maximum, which means that the speed is also at a maximum. What that means is that block P is moving at its maximum speed when block Q is dropped on top of it, and then boom, the speed goes down. that means that the maximum kinetic energy of the system just went down. That is because block Q added mass to the system. So, to conserve momentum, the velocity had to go down, which now means that the maximum kinetic energy of the system just went down. The maximum kinetic energy went down. That means that the maximum spring potential energy also goes down. The block spring system has maximum kinetic energy at the equilibrium position, and when it stretches out fully, that kinetic energy is converted to spring potential energy fully because energy is conserved. So, if I start off with less kinetic energy than I had before, then my spring potential energy is also going to be less than I had with the one block, because I have less kinetic energy to convert into spring potential energy. If the spring potential energy went down, what that means is that the amplitude also went down, because spring potential energy equals 1/2 kx squared, where x is the displacement from equilibrium, and in that case that is our amplitude. So if the spring potential energy went down, the amplitude also has to go down. Okay, so I'm gonna go over the scoring guidelines just to kind of give you an idea of what they're like really looking for you to write in this paragraph and how you can get those points. Okay, so first of all, this paragraph does not have to be a super long paragraph. Like, they're really just looking for some super specific key points, and you can get that done in just a few sentences, honestly. The correct answer was that the amplitude of PQ is less than the amplitude of block P alone, which is what we got. So, here, super key. Note, the response is graded even if an incorrect selection is made. So even if you pick the wrong thing, you can still get points. And I'll show you how you can do that. So, the first point, for applying conservation of momentum to the collision. So, if you say momentum is conserved, you get a point. That should totally be like a go-to statement for you. If you see a collision, then you should definitely say that momentum is conserved, unless it says otherwise. Second point is for correctly finding that the post-collision speed has decreased, or you can do some calculations to find how much it has decreased. In my opinion, when you're in a time crunch, personally, I wouldn't prefer those calculations, but I mean, if you like math, you can do it. But really, all you have to say is that the post-collision speed, so after the collision happens, the speed of the blocks goes down. That's all you have to say. Here it says, the first 2 points can be earned for stating that the collision is inelastic. So you could literally just say, the collision is inelastic, and you get 2 points. So by seeing the word stick in the problem, that's why I was like all about the word stick. If you say that the collision is inelastic, you get 2 points. Third point, for stating or implying that the system's kinetic energy has decreased. So previously you got a point for saying that the speed decreased, but you also need to connect that to the fact that because the speed has decreased, the kinetic energy also decreases. So you have to connect the speed to the kinetic energy. Next point, for stating or implying kinetic energy of blocks right after collision equals maximum potential energy of spring. Basically what they're getting at here is conservation of energy. So here you could write that the total energy is equal to 1/2 Ka squared, And that's saying that the total energy equals the maximum spring potential energy. So really, you just need to say that energy is conserved. Okay, next point, for stating or implying that the maximum potential energy is reached when the displacement from equilibrium equals the amplitude of oscillation. Okay, so they're like super energetic about this energy stuff. They know you have the potential to write a good paragraph, and they really just want to know that you know that potential energy is at its max when the spring is at its farthest from equilibrium, or at the amplitude of oscillation. And finally, for a logical and relevant and internally consistent argument that addresses the required argument, okay, so literally to get this point, you just make your claim at the beginning, whichever one you decided to pick, even if it's wrong, and then you just write a paragraph that supports it and sentences make sense. Okay, so if you're taking the test and you manage your time poorly like me and you have 5 minutes left and you need to write this paragraph, this is how you still get a decent amount of points on it. So when I took this, I did not have enough, or when I took this, I didn't have time to think about which amplitude was bigger or if they were equal or whatever. I just read the question and tried to write things that I knew were going to give me points. So for instance, the word stick is a huge red flag. They definitely want you to talk about momentum, conservation of momentum, and inelastic collision. That's totally 2 points right there. You can easily get, even if you have no idea about the amplitude thing. The other point that would be pretty easy to get is talking about conservation of energy. And finally, the other point that you should definitely be able to get is for writing a logical, clear, and coherent paragraph. So if you just write a paragraph that kind of has some structure and sort of makes sense, even if your claim is wrong, you can still totally get that point. So here, as you see, you'll totally get a lot of the points, even if your answer is incorrect or you don't have enough time to really think about what your answer should be. If you just hit on the points that are almost always given, like conservation of momentum, conservation of energy, writing a clear and coherent paragraph, you can still get several of the points. Hope that helped. I hope you guys are having a momentous day, and I hope you guys have lots of energy, especially because I know you have potential energy. Okay, bye!